if we're going to do the greatest common factor here on the first one, considering the numbers involved in the terms, you've got 6, you've got 9. The biggest number I can think of that goes into those evenly would be 3. So take a 3 out. As far as the variables are concerned, we've got x's and y's over here, we've got a's and b's over here. Variables are not shared in common between the two terms. So those variables have to stay put. Greatest common factor between these two terms is simply going to be 3. So we take 3 out. Now, the number of terms I start with here, I have to appreciate that what's going to be inside the parentheses over here, the leftovers, there has to be the same number of terms. So if 3 pops out, take 3, divide to 6. 2 is left here with an x and a y. Plus, 3 goes into 9 3 times. So there's a 3 here on the second term with an a and a b. We factored that completely by taking out the greatest common factor. So if we move to the next one, got 2 terms. As far as the numerical values are concerned in the 2 terms, you got a 2, you got an 8. So 2 would go into each of those. And on this one, you've got an x that is shared between these 2 terms, so I could take an x out as well. What's left is going to be 2 terms inside. As far as this first term is concerned, 2 goes into 2 one time. You took 1 x out. There were 2 x's there, so there's 1 x left. Plus, all right, for this second term, 2 goes into 8 4 times. You took 1 x out. There was 1 x there. No x's would be left. There's your factorization, your complete factorization for the second one. Okay, third problem. 2 terms. Numbers involved, 3 and 10. Greatest common factor between 3 and 10 would be 1, right? So really can't take anything out there. But we notice you got an a present in both terms, you got a b present in both terms. So a and b pop out. As far as what's left, for this first term, a and b are gone, so 3c is left. For the second term, a and b are gone, so we've got minus 10 left. All right, fourth one. Greatest common factor for the numbers would be 7. Take 7 out. You've got an m and an n present in both terms. So 7mn would be the greatest common factor we take out, meaning take 7 divided 14. We've got 2 left here. Took 1m out, right? There was 1m there. Took 1n out. There were 2 n's there, so there's 1n left. Then minus, this is where it can get tricky, but remember, there's got to be 2 terms left. Minus what? Okay, it's just going to be 1, right? Got to have something there to hold that place value. We took all of this out, so 1's going to be left. All right, last one. Got 5 and 2. Nothing working for me there. Let's see, the first term has an R and an S. The second term has a TUV. Nothing's shared, is there? Yeah. You can't factor the last one. So since you can't factor the last one, what we say is that the last one is prime. You take the greatest common factors a step farther. Notice we have a couple of products here separated by addition, right? We have this piece multiplied, we have this piece multiplied. So really what we got going here is the same as what we had on the previous page. You had a bunch of stuff multiplied, added to another bunch of stuff multiplied. The thing is, you want to take out what's in common between these pieces. So what's in common with these products is the x minus y's, right? So I can take an x minus y out. Now, when I take an x minus y out, taking it out of this first position, 6 would be left. taking it out of this second position, it's gone from here, 7a would be left. So I add on the 7a because I started with addition in the first place. That would be the factorization on that one. So if you look at the next one, we've got subtraction. Subtraction is separating a couple of, well, products. Got this piece multiplied here. You got this piece standing alone. So realistically, with that second piece, you could think of there being a little 1 here in front, right? That's multiplied on. That little 1 becomes significant when you try to factor this one because you have a quantity of 3x plus 2 that's in common between both of these parts. So I take 3x plus 2 out. Second set of parentheses, that's the leftovers. So the leftover from this first part, since 3x plus 2 is now gone, that first part we've got a 4b left. And we are subtracting. And we took the 3x plus 2 out of this part. That's what now makes that 1 significant. 1 would be left over here. That's just another take on greatest common factors. Okay, so when we have 4 terms and we're looking to factor, the first rule is always look for the greatest common factor. But I think you'll find on these greatest common factors will not apply. So when you have 4 terms, usually what we do is we do some grouping. We factor by grouping. And we set up, kind of 2 separate problems here where you're looking for the greatest common factor in this piece and the greatest common factor in this piece. So if I look at the greatest common factor in this first piece, I've got 4 and 6 involved, so 2 I would take out of that. You've got a p to the third, you've got a p to the second. So as far as the greatest amount I could take out there with the p's, I could take out 2 of those, right? Because at least 2 are present in each term. I take 2p to the second out of this first set of parentheses, meaning what's left over, well, let's see here. 2 goes into 4 here, you got 2 left. Got p cubed to start, but now you've taken 2 p's out, so there's 1 p left. It's minus 2 goes into 6 3 times. You took 2 p's out from this one, right? So there's no p's left. That's the factorization for this first part of the grouping. Now, for the second part. Second part, you've got 2 terms. You've got 6 and 9. You know 3 goes into both. So we'll take out a 3, and we'll make it a plus 3. Right? Makes sense to take out a positive 3. As far as what's left, well, 3 goes into 6p here, 2p times. And 3 goes into 9, it's a negative 9, so minus 3 times. Notice how this little part here in the parentheses compared to this little part in the parentheses, it's the same thing. Whenever we do factoring by grouping, that's our goal, to have these little sets of parentheses match up. Because if they do, we just do what we did on the previous slide. You take that 2p minus 3 out. You take that out, and if you write what's left, you've got a 2p squared here plus a 3 over here. There's your factorization. Now that we've moved a little farther into this, it's nice to understand too, you can always check by multiplying all this out. If you multiply all this out, you'll get back to this original part. We could have done that on any of the previous problems so far. All right, try the next one. 4 terms, we group them. Start with that first grouping.
Are you always going to group the first 2 and the last 2?
Yeah, normally if you group the first 2, you group the last 2, it's going to work. You could reshuffle these terms though, and it could still possibly work.
What does like 5
Does 5 terms, well, that's a whole other category. We'll explore that another time. All right, taking the greatest common factor out of these two terms. What's the greatest common factor? 3x squared, right. So 3x squared pops out. As far as what's left, well, let's see. 3 goes into 15, you have 5. Took 2 x's out, there were 3, so here's 1. And then you took 3x squared out here. Since you're subtracting, we got to write minus 1. So as we discussed on the previous problem, for this next grouping, if this is all going to work out for us, we need a 5x minus 1 inside the parentheses, right? So can we create that out of this grouping? I'm hoping so, right? Take 4 out, maybe? In fact, make it a negative 4, because that'll change your signs here, which we have opposite signs over here. Take a negative 4 out. That should work out. Take the negative 4 out. Got this grouping here, this grouping here. Greatest common factor between each is the 5x minus 1. We pull that 5x minus 1 out. And the leftovers, you got 3x squared minus 4. All right, let's try one more here. One more, and then we'll move on to the next type. This 20n cubed plus 4n squared plus 5n plus 1. All right, in the first grouping, what's the greatest common factor? 4n squared. 4n squared pops out. As far as that 20n cubed is concerned, you've got 5n left there plus 1, right? Now, in the second grouping, remember, when we factor that, we now know we want a 5n plus 1 left over. So we have to take out 1, right? Because we already have 5n plus 1 there, so take out a 1. You take out that 1. Got this grouping here, this grouping here. 5n plus 1 is in common between the two. We move that into the lead position, leaving us with 4n squared plus 1. All right, so if we're going to split this up, understanding that this kind of answer comes from foiling out a couple of binomials. Well, let's think about, again, how we would foil this out and how we would arrive at this answer. Usually what would happen is you would multiply the first terms in your binomials to get that first term there. Eventually, your outside and inside terms you would have to add together, combine together to get this middle term. And then normally the way it works out, you multiply the last terms in the binomial to get that last guy. Here's what's really nice about these types of problems on this slide. Lead coefficient is 1 on all these. That really makes it easy. When we switch that 1 up, that's when it gets more challenging. So, as far as factoring goes here, I'm starting with an x squared. I know that's a result of multiplying the first terms in each binomial, so I put an x here and x here. X times x is x squared. And then I move my attention to this last term, and I create combinations that multiply to give me a negative 50. This sign is significant. And I check by multiplying the outside and the inside to get back to this negative 5. So if you choose, say, negative 10 and positive 5, those last terms multiply to give you negative 50. So that checks out. But then ultimately how it checks out again, take x times positive 5, take negative 10 times x. You got a negative 10x, you got a positive 5x. That goes back to give you that negative 5x there. So there's your factorization. The it's really nice when you got a 1 in the lead position. So if you look at this second one, breaking this up, we're dealing with n's. So n times n in the lead spots gives you n squared. Looking at this negative 24, thinking about factors of negative 24. Also in the back of my mind, outside, inside terms have to give me a positive 2 back. So it makes sense if you use what? Positive 6, negative 4, right? You check through foiling, that should give you that, that plus 2n there as the middle term. There's your factorization. Okay, we're spicing things up now. We threw an extra variable in here on the third one. I think we can handle it. Okay, if the pattern holds true, we've got an x in the lead position here, an x squared in the lead position here, so need x's in the lead position in each of the binomials. X times x gives you x squared. Now focus your attention on that last term. Looking at that 12. Got a lot of positive stuff happening here, right? So what multiplies to give me 12? That would make sense here. 6 and 2 be plus 6, plus 2, and since this is a y squared on this 12y squared, we need to make sure we include y's on the 6 and the 2. Once again, check through foiling. Outside you've got 2xy, inside you've got 6xy. Hey, what do you know? Put it together, that's 8xy. All right, last one, you've got m squared minus 5m minus 6. Setting up the two binomials. Dealing with m's, so we'll put those in the lead positions. Not too many options here for factors of 6, so it's either going to be 2, 3, 6, 1. What's your preference? Negative 6, positive 1. Right? Outside would be 1m, inside would be negative 6m. That combines to give you negative 5m. All right, let's see if we can do these when that lead coefficient, though, is not a 1. All right, and these are the ones we'll end with for today. We're reversing the FOIL process. So two binomials. If I multiply the first terms, they're going to give me 4n squared here. I multiply the outside and inside, then combine them. That's going to give me the negative 17n. Multiply the last terms. That's going to give me a positive 18 back. Let's see if we can create that combination over here with a pair of binomials. Okay. How do you know where to start? Well, normally, when you've got something prime here or prime here, that's where I start. Don't have anything prime, do we? So we just kind of have to gut it out and play with something. The more you do these, the easier it becomes to see the combinations. So things that multiply to give me 4n squared, maybe 4n and 1, right? 4n and 1n. If I put those in, and now focus my attention in on this 18, well, all right, things that multiply to give me 18. I just start playing. Maybe I put 9 here and 2 here. Right, that multiplies to give me 18. Now, as far as the outside's concerned, if it helps, draw it out. This would be 8n, right? This would be 9n. If I put those together, would that get me to that 17? Well, it would. If those were negative, right? Can I make those negative? Sure I can. I can make those negative right there. But you do have to be careful on those signs and always go back to checking this last little product. Negative 9 times negative 2. Has to check out to give you that positive 18 for that to work. And it does. So your factorization is 4n minus 9 and n minus 2. Just happened to guess right on that first part, right? Let's try the second one. Okay, on the second one here, we're looking at the 6x squared to get started. Obviously not prime, so we got some possibilities. We could do 6x times 1x. We could do 2x times 3x. Doesn't matter to me. All right, 2x times 3x. So now we focus our attention on the negative 70. So thinking of things that multiply to give me 70. And 7 and 10 probably come to mind pretty quick, right? 7 and 10 going to work out here? No? Not going to work? Don't think so? Let's see, that's going to be 20x. And that's going to be 21x. I'm trying to get back to 1x there, right? I think something's going to happen here, because this could be positive and this could be negative, right? So how's that going to work? That's going to make this positive 7, minus 10. All right. Doing well. We're efficient. All right, on the last one, this is where I was talking about prime numbers before. I think the last one's a little nicer. It's a little nicer because as far as playing with values are concerned, you know that eventually in the last position, you want numbers that multiply to give you that 3. So it has to be 1, it has to be 3 here. Now in the first position, you got that 10k squared. So we think in 10 and 1, we think in 5 and 2. What are we thinking? Okay, 5 and 2. 5k, 2k. Outside would be 15, inside that'd be 2. We're trying to get back to 17 here. It's all positive, we can do that. There's your factorization.